Have you ever wondered if the universe has a rule book? A set of absolute laws that everything has to follow, from the biggest stars down to your morning coffee? Well, it does. It's called thermodynamics. And trust me, this isn't some dusty, boring textbook topic. It's the secret code that explains how our world actually works. So let's get into it and start decoding the universe's rulebook. Just think about a few things you probably use every single day. Let's start with your car. That engine is an incredible piece of work, right? It takes the chemical energy locked inside fuel and turns it into the motion that gets you from A to B. Or how about your refrigerator? It's sitting there in your kitchen, performing what seems like actual magic. It uses energy to pump heat out of a closed box, keeping your food cold even when the room around it is warm. And let's get even closer to home, your own body. It's this incredibly complex biological machine that's constantly, every second, turning the food you eat into the energy you need to live, to think, to move, to do everything. So you've got a car engine, a fridge, and your own body. On the surface, they couldn't be more different. But what if I told you that they all operate under the exact same, universal, totally non-negotiable set of rules? Well, that's where thermodynamics comes in. At its heart, it's really the science of how energy moves and changes from one form to another. It's not worried about the tiny details of every single atom. It looks at the big picture, where things start and where they end up. And from that, it lays down the law. And believe me, these laws are universal. They apply to absolutely everything in existence. I'm serious. From the smallest particle to the biggest galaxy, nothing gets a free pass. Now, to really understand these cosmic rules, we first need to learn the lingo. Thermodynamics has its own language for how it carves up the universe to study it. So let's get the basics down. First, we have to define a system, and that's just the part of the universe we're interested in at the moment. An open system, like a big steam turbine, can exchange both energy and actual stuff, matter, with its surroundings. A closed system, like that refrigerator we talked about, lets energy pass through but not matter. And then you have an isolated system, which exchanges absolutely nothing. And what's the ultimate isolated system? The entire universe itself. Okay, next, we describe these systems using properties. This is pretty intuitive. Intensive properties are things that don't change no matter how much stuff you have. Think about it. A single drop of boiling water has the exact same temperature as a whole giant pot of it. But extensive properties, like volume or mass, totally depend on how much stuff you've got. More stuff means a bigger number. Simple as that. All right, now that we've got the language down, it is time for the main event. These are the 4 cosmic rules that everything, and I mean everything, in the entire universe has to obey. No exceptions. And we're going to start with a law that's so fundamental they actually came up with it after the first and second laws. They realized they'd missed a really basic assumption, so they had to go back and call it the 0th law.
Kind of funny, right?
Okay, I know, that sounds like a complicated logic puzzle, but the idea behind it is actually incredibly simple, and it's something you rely on all the time without even realizing it. Here's the simple version. This is why thermometers work. That's it. If a thermometer tells you your coffee is 90 degrees and then it tells you your tea is 90 degrees, you know that the coffee and the tea are at the same temperature. They don't even have to touch each other to know that. That's the 0th law in action. And this whole idea of equilibrium and energy transfer leads us directly to probably the most famous law of them all, the first law. You've probably heard this one before. It's the law of conservation of energy, and it's a cornerstone of all physics. You simply cannot create energy out of nothing, and you can't make it vanish into thin air. All you can do is change it from one type to another, like a power plant changing the chemical energy in coal into the electrical energy that powers your home. So a good way to think about it is this. In the great casino of the universe, you can't win. The total number of energy chips is fixed. You can trade your chips around, but you can never, ever walk away with more than the universe started with. You can only break even. But that raises a question, right? If the total amount of energy never changes, why does everything seem to run down? Why do our cars need more fuel? That question leads us to what is maybe the most profound and definitely the most misunderstood law of them all. This is where things get really, really interesting. The answer is all in the second law of thermodynamics. You see, while the first law tells you that you can't win, the second law comes in with even tougher news. You can't even break even. This law introduces a critical concept called entropy. And what it says is that the total entropy, you can think of it as disorder, of an isolated system like our universe can only go up. It never ever goes down. This is the universe's one-way street. It's the arrow of time. It's why things get old, fall apart, and cool down. So what exactly is entropy? Well, people often call it disorder, but a better way to think about it is the spreading out of energy. Energy always, naturally, spreads out from being concentrated and useful to being spread out and useless. Your hot cup of coffee doesn't just spontaneously get hotter by sucking heat out of the cool air in the room, right? No, the heat always flows out of the coffee, spreading out until everything is one lukewarm temperature. And that's why you can't build a perpetual motion machine. You always lose some energy to useless, disordered heat. This is a fantastic way to picture it. On one hand, you have a perfect ice crystal. That's low entropy. The molecules are locked into a beautiful, ordered pattern. Its energy is concentrated. But when you add heat, it turns to steam. Now the molecules are just flying around chaotically, filling up the whole container. The energy is spread out everywhere. That's high entropy, total chaos. And this unavoidable march towards messiness brings up another question. If messiness is always increasing, is there a limit? Is there an ultimate point of maximum order? And that very question brings us to our final cosmic rule, the third law of thermodynamics. This is the one that defines the ultimate limit, the absolute rock-bottom temperature for the entire universe. So in simple terms, the colder you get, the more orderly things become. As you get closer and closer to the coldest possible temperature, that's absolute zero or minus 273.15 Celsius, the random jiggling of atoms basically grinds to a halt. At that point, the entropy of a perfect crystal would theoretically be zero, a state of perfect order. Now, we can never actually reach it, but it sets the absolute floor for disorder in the cosmos. And this all leaves us with one final, gigantic cosmic question. If the second law says that the total disorder of our universe is always going up and up, what does that mean for the far, far future? What happens when all the energy in the universe has spread out completely evenly and everything is at the same lukewarm temperature? It's a thought that takes us all the way from a humble refrigerator to the ultimate fate of everything, a quiet, final equilibrium that some call the heat death of the universe.